My name is Claudia Gomez and I'm going to talk to you about the image intensifier tube. The image intensifier tube, we can find them in the fluoroscopy C-arm. We have them right above the patient. The X-ray tube will be underneath the patient. The image intensifier receives the signal and will produce enough brightness or luminance in order for the monitors to display it, and we will be able to see them clearly. The image intensifier tube is an electronic device that receives the image forming X-ray beam and converts it into a visible light image of high intensity. The conventional fluoroscopy without image intensification has two limitations. It produces an inferior image and the light is too dim for phototopic daylight vision. Before, the radiologists, when they did the fluoroscopy, they had to go into a dark room in order to see the images because they were not bright enough to see them outside in the OR. So they had to go into an OR, special room, a dark room, where they had to see these images. Now, with the image intensifier tube, they're able to see them because it gives more brightness to the image. So the design of the image intensifier tube is an evacuated glass envelope, and we can see the glass envelope around it. Also known as the vacuum tube, which provides structural support, maintain the vacuum tube, which has a metal housing or container to protect the tube from breaking or rough handling. So it's basically to protect everything that's inside the tube. The vacuum contains the input phosphor screen, the photocathode, the electrostatic lenses, the anodes, focal point, I will explain everything later, and the output phosphor. So the input screen, which is this one, this first layer. Actually, the input screen and the photocathode are stick together. So it's the remnant beam radiation interacts with the input phosphor screen, which contains cesium iodine. And here is where the energy of the X-ray photon is converted into visible light. So the X-rays come here, they strike the input phosphor, which is a concave screen, and the input phosphor screen is the one that's in charge to take those X-ray photons and convert them into light photons. The CSI crystals, which we're going to see here how they look like. These are the arrangement of the crystals. So the CSI crystals on the input phosphor are approximately 5 micrometers in diameter and they're packed tightly. This results in microlight pipes. These are the little pipes with little dispersion, and this design improves the spatial resolution. Then we have the photocathode. So X-rays hit the input phosphor screen. This converts the X-ray photons into light photons, and then the photocathode is the one that's going to convert those light photons into electrons. So the distance between these two, the input screen and the photocathode, as I was saying earlier, it's minimal. The photocathode is bound directly to the input screen by a thin layer of adhesive that is transparent. The photocathode is made up of a combination of antimony and cesium compounds. Its function is, as I said, to emit light from the input screen and convert it into electrons, or also called photoelectrons. This process is called the photoemission or photoelectric emission. So X-rays, input phosphor, photocathode, and right here we already have the electrons. So the electrons will go in the X-ray beam in an in the electron beam and will be accelerated by the electrostatic lenses. They are located like around the glass envelope, and they will help the electrons to keep the track because they have a negative charge, so they repel the electrons, so the electrons will continue in the same path. Then we have the accelerating anode, which are right here, the anodes. They are located at the neck of the image intensifier. They're circular plates with a hole in the middle so the electrons can pass through the output phosphor screen. The accelerator anode draws electrons from the photocathode and accelerate them towards the output screen. They have a potential difference of 25 kV. Then the electrons will hit or will strike the output phosphor screen, which is this little one. The energy is converted back into light photons on the screen, a lot brighter than the input phosphor due to its smaller size and additional energy given to the electrons when they are accelerated through the image intensifier. This is made of zinc cadmium sulfate, and they range about in measurements in size about 1 inch, 2.5 centimeters to 1.5 or 2 inches. Now we have the flux gain, which are now how we're going to measure how many X-ray photons come into the input screen and how many go out the output screen. So the flux gain is the considerable amount of light at the output phosphor. It produces almost 50 to 150 times as many light as were in the incoming X-rays. The ratio of the number of light photons at the output phosphor to the number of X-rays at the input phosphor is called the flux gain. For each light photon emitted from the input screen of the intensifier tube, an average of 50 light photons are emitted onto the output screen. So 1 X-ray photons to 1,000 light photons to 50 photoelectrons to finally convert them into 3,000 light photons. So we find the flux gain by the formula, the number of output light photons over the number of the input X-ray photons. That's how we find the flux gain, and it's almost going to be always going to be like 50 times more. Of course, it actually depends. It fluctuates, but it depends also in the manufacturer, but it has to be around that range. The magnification gain is the square of the input screen diameter over the square of the output screen diameter. And basically what the magnification gain here does is the larger the field of view we choose, the more brightness the image is going to have. The smaller field of view we choose, the less brightness the image will have, but it will have a better resolution. So for a large field of view, we have that the magnification gain is higher, the output spatial resolution is lower, the image distortion is higher and the radiation dose is lower. On the other side, the smaller the field of view, the magnification gain is lower, the output spatial resolution is higher, and the image distortions are lower, and the radiation dose for the patient is higher. So the smaller the input screen we choose, the better resolution, the more patient dose, the less brightness the image has. And again, it's the input of the diameter of the input screen to the square over the output screen diameter to the square. Okay, this is basically how the image will look like without the brightness and with brightness. Okay, and finally, the brightness gain is defined as the ability of the image intensifier to increase the illumination level of the images. The increased illumination of the image is due to the multiplication of the light photons at the output phosphor compared with the X-rays at the input phosphor, and the image magnification from the input phosphor to the output phosphor, which is magnification gain. After the output screen emit light photons, they will be directed to the beam splitter, which is, I will show you here. It's a little splitter here that is connected to the intensifier tube that will divide that signal into different recording methods or modes. One is the TV monitor, the other one is the cine camera, and the other one is the picture spot film and picture camera. Now the digital intensifier tubes have what we call CMOs or CCDs, which are very little plates, and this give the signal right away. They send the signal right away to the display monitors. They're faster, they have a better resolution, and they're easier to handle. Okay, patient dose. As I was explaining before, the effect of the image intensifier or field of view, if it's the field of view is a large field of view, the patient dose is going to be minimum, and if it's a small field of view, it's going to have patient dose that it's higher. For example, the field of view in a 17 centimeter diameter input screen is 0.6 milligrays per second, and the field of view in a diameter of 12 centimeters, which is a smaller field of view, the dose rate will be 1.23 milligrays per second. So it's a lot of dose for a better resolution. So the field of view will decrease and the dose delivered to the patient's skin will increase. That's basically it. Thank you very much.